So I really appreciate the invitation from UNC Chapel Hill, from RENC, from Duke and NC State for allowing me to come give you a distinguished lecture on massive scale streaming analytics. And I'm really excited about this topic, so if you have questions, please let me know. Ashok already mentioned a lot of my background, and I just think this is an exciting area, and now it's come of age. So you hear a lot of folks talking about analytics at scale, and it's something not just for academia, but for industry as well, for governments, for national labs. It's just an exciting time to be in this area. So I want to tell you first a little bit about Georgia Tech, where I'm a department chair in a department that's focused in this area, and then tell you a bit about the work that we've been doing in streaming analytics, and hopefully get you excited to do more work in this area as well. So we're organized a little bit differently at Georgia Tech, and I have this new school of computational science and engineering where we try to look at these real-world challenges. So I'm not going to spend too much time telling you about Georgia Tech, but the areas that we focus on are just synonymous with this new approach of looking at visualization, cybersecurity, big data, high-performance computing, machine learning, and putting it all together to solve real-world challenges in this sort of big data analytics phase. So once you've collected up all of this information, what do you do with it? How do you figure out how to get value out of it, intelligence from it, and then how do you change the world? How do you make it a better place? So the real payoff comes when we start looking at application areas related to, say, epidemiology. I know that there's a great biomedical program here, social networks, bioinformatics, security, etc. All of these application domains are places where we may want to take information that we've collected that's coming at us and try to make decisions in near real time. So I have a great faculty in my department or school, about 20 or so faculty members, a lot of research. And we run a number of programs, both for undergraduates looking for a summer research experience, and also we have a number of master's and PhD programs where we've defined what we believe it takes to have a student proficient in this new area of computational science and engineering that includes large-scale machine learning, high-performance computing, numeric methods, and other types of data analytics. So let me move on to the heart of my talk, which is to tell you about the massive scale streaming analytics and the flavors that we're looking at. I like to call this our STING initiative because this is our Georgia Tech mascot. It's that yellow jacket over there who likes to sting. But it's kind of nice that STING also stands for Spatio-Temporal Interaction Networks and Graphs. So one way we like to view information is by using what we think of as a attributed relationship graph where we have vertices and we have edges. And the vertices are typically the nouns in the system, the objects, and the edges are the transactions or interactions among them. And this is a pretty nice abstraction for trying to solve a lot of different types of globally significant grand challenges. I have a few on the board up here. For instance, looking at large evolving social networks, we'd be interested in tracking communities and as they change over time. Or in this day and age, we have to be cognizant of cyber-based attacks, and we want to look at identifying and giving attribution to different types of attacks based on network traffic. We have insider threats within organizations is a very real problem. Improving our electric power grid and its resilience so that when lines and transformers go down, we don't lose half of the US power grid. And then in Atlanta, we're very concerned about health. We have the US Centers for Disease Control and Prevention, the CDC, located in Atlanta, where we're interested in trying to track and detect and prevent disease within human populations. So these are just the hallmark of some of the types of large-scale problems where we have information coming from sensors, from different sources, and it's coming at us in large rates, often in near real time. And at the end of the day, what we want to do is help people become or remain safer, protect them, and make the world a better place. So it's really a important problem space to look at. And these are different types of applications than traditionally where the high-performance computing and scientific computing communities have developed over the last several decades. So traditionally, we have applications that have dense floating point operations are very regular, and we can just take that problem and put it on a cluster, a cloud, some of today's petascale machines, and try to scale it up with traditional methods, and typically they do very well. But the hallmark of these types of problems is somewhat different. When I take these problems and try to parallelize them at scale, I run into some research challenges. The problems are often sparse and lack the locality that I have in the more traditional applications like fluid dynamics, molecular dynamics, and others. I have data in motion, it's streaming. I want to be able to keep up with that stream in near real time to make decisions, often in milliseconds. I don't want to wait for a batch queue for hours or days, or have to wait an hour to ingest my data if I need to make an immediate decision. And I also have to worry about energy efficiency of the system. As we know, power is a driving cost, sometimes more expensive than the machine that's it's driving. I have to look at resilience of the machine and the platform. It has to be easy to program. So an analyst, not a computer scientist, but an analyst can program for their application and get it all running. So this is the initiative that I'm leading up at Georgia Tech. And we have a lot of support from various agencies and various types of problems. But the nice part about it is we've been able to apply a graph abstraction to many of these problems. And if we get that graph abstraction right, then we can solve a lot of these real-world problems. So that's the challenge that we're looking at. So not all big data problems need graph analysis. So I want to throw that out there that I'm not Mr. Graph entirely, but I believe graph analysis will enable a certain set of the analytics to run efficiently. And of course, there's large-scale machine learning that I believe in, and some other areas that will help as well. But for this talk, I'm going to focus a little bit more on graph analysis because that's one of the unique capabilities that we have. So I already mentioned a couple problem areas, but if I dig a little bit deeper in healthcare, we may be trying to find outbreaks of disease. In business intelligence, we may be trying to figure out how to make decisions at scale. In systems biology, we may be looking at drug design. And in simulation, I may want to simulate whole populations looking at socioeconomic and political models. And as I said, the graph is a nice abstraction because I can take my nouns in the system, the objects, and make them vertices. So I have vertices of different types. And then I'll take the interactions among them and make them edges. So there may be different types of interactions. The interactions may occur at certain times, so I may have timestamps. And I can have a very rich graph based on that. So graphs are really a unifying motif for this data analysis. And instead of just a static graph like what we learn in our undergraduate computer science textbooks, we're really interested in the fact that this data is always bombarding us, always coming to us from sensors, and we want to make decisions on the graph as it changes over time. So for the first time, we're looking at analytics where they were fully dynamic in nature, and there isn't a lot of literature on it. So for instance, we're often used to taking a graph, and if I asked you program an algorithm or design an algorithm and implement it to find the connected components, I'm sure all of you could do it. But if I tell you, give me an algorithm that tells me anytime a new community forms over time, we don't have a lot of literature that tells us the hardness of those problems or how to do it. So we're looking at trying to catalog more dynamic algorithms on graphs that change over time. The other challenge is that this is different from an online algorithm or a static algorithm where if I give you an input and I tell you what I want solved, you can solve it and you can repeat it and get the same answer. Here, often, I have no start or end time. I'm bombarded with data, and at the end of the day, a correct algorithm may mean something different. By a correct algorithm, what I want to do is enable a human to make a better decision with the best information I can supply them in the time constraint that they have or I may need to operate in milliseconds. If this is, for instance, a cyber attack and I want to detect it and stop it, I only have a very short time to react. So at the end of the day, correctness just means that, we have some papers that formalize what we mean by correctness, but it's a different type of regime where we want to have real-world decision-making and do that rapidly and try to improve the state of the art in that area. So any questions before I keep going? There's a pop quiz at the end, so make sure you ask. Okay. So data rates, I'm probably preaching to the choir, but everyone here knows that data rates and volumes are just immense and growing. Facebook has over 1 billion active users. People have an average of 130 friends. There's over 30 billion pieces of content shared per month. Like it or not, there's lots of tweets out there, and some people argue that they have value, others not, but that's a lot of data to look through. The internet is just hordes of data going past, and these are just some of the sensors that you may think about, and there's others out there. In this day and age, everything that we do is generating a data trail. Our smartphones have GPS or tracking what we do. Everything is capturing our daily lives. And that information then is often fed into these graph analytics. So the difference is that historically, as I mentioned before, you would take your, for those who don't know, this is a punch card. You would take our DestiDeck, our program, and our data, sort of put it together, and we still do this today with supercomputers, where we put that into a batch queuing system. The supercomputer then crunches it, very good machines, and gives you an answer out. And you have your answer, and it's very static, and you look at what you have, and you like it or you don't like it, and then you go back and you may submit another job to the queue based on that. Whereas today, when I talk about massive scale streaming analytics, it's more like the data vortex on the right, where information is just flying past us. And what I want to do is tap into that stream with my analytics and make decisions on the fly. And there's no start time, end time. I really need to come up with a system that's able to tap into that to make our decisions. So there's a lot of fundamental computer science research that's needed to identify what are analytics that we can run, what are their capabilities and complexities, and how do we come up with an analytic platform that's able to implement this and be easy to program, etc. So as I mentioned, our focus is on streaming graphs. So the idea that we have is, for instance, here's a physical being, a person. She happens to be on Facebook, so maybe that's person A. And as an example, at time 1, T1, she pokes person B. Well, here's person B, and maybe at time 2, she sends a message to person C and sends that off. And oh, at time 2, person B received the poke from person A. So what we have are real-world actions in this example. And I could go on in time. Maybe at time 3, she views a wall post on person D's wall. At time 4, she posts something, and maybe he at time 3 is viewing her wall and then sends her a message at time 4. These are happening in massive rate concurrently. And what we do is we take these type of tuples and we turn them into an edge stream where we have billions of edges, and this is where we go through our graph abstraction from the original domain into something more abstract like these edges of a graph. And what we'd like to do is just funnel those into a big supercomputer. And that supercomputer now thinks about this graph in terms of vertices and edges. And I've used some colors here to represent different types of vertices, different types of edges, or the attributes on those vertices and edges. And then I have a bunch of analysts, really smart people, and they're the ones with the good questions. They may want to ask a question of that graph, and they'll formulate it in terms of some abstract graph query. They'll go to the graph where it can execute very fast, and then they may get some result that they have to then sift to the real data to see what's actually happening. For instance, they may be looking at change detection in the graph, flows, clustering, centrality, structural changes in the graph, key actors, anomalies in the graph. These are all sorts of features that I can find very easily in the graph structure that may be harder to find from just the original data piled up on top of me. And not only do they have the first question, but as they look through the graph, they may have a second question, a third question, many questions concurrently. So my challenge is to come up with an analytic platform, a system, where I can ingest and have essentially one writer process to ingest this data logically, and then multiple concurrent reader processes. They're able to run the analytics, some of them persistently, like change detections, where I'm looking for maybe a structural change in the graph. And I want to keep up with that in near real time for billions of edges streaming in. So that's the challenge. If I look at graph analytics for social networks, I may, this is an example where I like to talk about Facebook because many of you know Facebook, use Facebook, even if you don't admit it publicly. And it's also a way to easily describe what we're doing, although we're not really in our lab looking at Facebook data. It's just an easy way to talk about things. So we may have vertices that represent people, events, fan pages, and then edges are the types of edges that I mentioned before, where every action that you take would generate an edge. Poking, viewing a link, clicking on a wall, sending a private message, reading that message, logging in, logging out. Every one of those is an action that we could record as an edge. And we can build up these massive streaming graphs over time that have that representation of what's been seen. So what we would like to do on a graph like that is find, we often want to find communities on the fly. Like I would like to find all Georgia Tech professors who like to drink Deer Park water. Well, actually in Atlanta we have Coca-Cola, so maybe I want to look for Pepsi drinkers and eliminate them. Oh, that wasn't recorded, was it? Darn. So we have some projects where we're trying to discover communities on the fly as they emerge from the data and track what happens to them. I want to find that a new community has emerged that may be very interesting to me from, say, a marketing standpoint or a security standpoint. Why is there a new community that's been stood up? What are they doing? Or maybe I'm trying to find a community that comes to life but doesn't interact with other communities. That may be very interesting. Why is that happening? I want to look for important individuals. Often I may be looking for folks who are very central or core to different communities or important actors. In some graphs that may be a congestion point. Maybe I'm looking at traffic flow and that's a hotspot that I want to try to alleviate. In many organizations we're looking for anomalies. However you may define an anomaly, I want to find outliers. I want to discover a community, look at what their general features are, and then look for outliers to those general modes that I would find inside of that community. Or given a community, I want to find a representative member of the community that I can hold up and I can run tests against and so on. Or given a set of individuals, maybe I want to find the best community that includes them or contains them. So in a social network setting, I can describe these, and often when we're defining analytics, I use terminology from social networks, but keep in mind that we're applying this towards data sets coming from a variety of sources, not just social networks. Any questions before I go on? Correct. So have we done any work on comparing communities? Yes, similarities against communities. Again, I can refer you to some papers. It's a very hard question. So there are many challenges. For instance, communities of different sizes. We can look at different characteristics of communities and see how much they overlap. There's the graph theoretic, looking at the distance between communities in terms of, say, edit distance. And we've looked at that somewhat, and I can talk to you offline. I mean, there's so many research questions. If you want to get like 25 PhD dissertations out of this type of analysis, I'm sure that's just the tip of the iceberg. Question?
Just curious what the graphs are. They specifically graphs at a particular time period, and then you're removing particular nodes as they expire, or are you just continuously building up this graph as time gets?
So excellent question. The question has to do with how do these graphs evolve over time. So if I go to my next slide, I'll come to that very very soon. So if maybe I'll talk about it and then I'll have some slides to back it up. I could think about this in different ways. I could create a graph at this time instance, and then when I get new information, create a new graph and look for the differences between them, and keep creating sequences of graphs. The hard part for that is I don't have the time or resources to maintain that history in separate data structures of graphs. When I traverse through a graph, I want to have it there readily so that my analytics can walk through it. At the same time, I'm updating the graph because in many of my problems, I just don't have the time to look at a graph and diffs or instances of it. So we've just decided that it's all going to go into the same graphs. Now, the more interesting question is, given a fixed resource like a computer with some amount of memory, even if I buy a workstation or an enterprise server with terabytes of RAM and my graph is in memory, at some point it's going to fill up. Once I'm running this over a day, a week, a month, a year, 10 years, at some point it's going to fill up. So we've started to look at what to do when you're in the regime where every time you put something into the graph, you have to kick something out. So you can think about that as steady state of figuring out what's important to keep, not just using a sliding time window. I could do that, and that's what a lot of people do today. But I want to decide when I ingest something into the graph, do I really need to put it in the graph, or can I just store it on the side and throw it away after a while? Or can I decide when I replace things in the graph, what is core structural pieces that I want to include? But the fact that I sent you one email or one Facebook message today, does that really matter 20 years from now? Probably not. So there may be some key things that I want to keep and some things that I don't. So that's a research question. I tend to think of it as being very domain specific. So once I get to working with an analyst or a particular domain, that may influence how we answer those questions. So streaming queries, I mentioned a little bit. We may look at graph metrics, and I think of a graph metric and how it changes as properties or characteristics that we would often compute on a static graph. So I may look at a shortest path and look at how it changes over time. I may look at say a score like between centrality of a vertex and how it changes over time. This is really looking at some metric that we know how to compute on static graphs and watching for a change. I may want to try to understand, are there patterns to the changes? Are there seasonal variations? Like, why was everyone watching the same TV channel last night? I may want to answer that. What are responses to events that happen, etc.? I want to figure out what those anomalies are. And what are temporal anomalies in the graph? Do key members in clusters or committees change over time? Are there indicators of event responses before they are obvious? So can I pick up these tells or these signals? For the insider threat problem, I may want to find that someone is doing some preparation because they're about to be fired from a company and trying to exfiltrate all the IP. They're copying out source code and taking their resume out and doing all these things. I may want to look for such events as well. So there's a lot of streaming work that we can have, and coming from a variety of application areas. Here are a couple more in cybersecurity. We do a lot of work in credit fraud forensics, trying to detect and monitor customers' data, working with a number of companies in the Georgia region, but also some companies around the world. Bioinformatics, power networks I've talked about. There's really a lot of problems out there that are enabled by graphs. Now, as an example, our group decided to see if there's any value to Twitter. And this was probably about 2009, and we're the first research group out there to take a full take of public tweets, same ones going into the Library of Congress, and we decided to try our hand at analyzing these tweets. So we took a fire hose of tweets, back when you could, and put it into a special purpose machine for graph processing, and we ran our analytics as kind of a proof of concept to see what emerged of trying to find the most important actors using a metric called betweenist centrality. Betweenist centrality is really looking at I'll have a definition in a couple slides, but it's looking for important actors, those who are very central to events where they just are essentially the top actors in events. If you remove them, they most disconnect the network. And there's a lot of public literature on why they may be important. In fact, it's conjectured if we could run this type of analysis, we could have picked out the terrorist on September 11th very easily from the data. So there's a lot of interest in this network. And we looked at two events that were emerging in September and October 2009, where we took 2 months, about 4 terabytes of data, and pumped it into this supercomputer. And one thing that was happening was an outbreak of a virus, H1N1, influenza. And the other thing that happened was a 500-year flood event in Atlanta. And I have some results for both. But because we've had a couple more 500-year flood events since then, maybe it's not as interesting. So H1N1, I'll tell you a little bit about it. This was a disease, that influenza, that the media and health officials were predicting would wipe out double-digit percentages of the world population. Scary, scary stuff. No vaccine yet for it. Wasn't sure how it would work and how it would propagate. Very much like well, we've had a couple different scares like that. Ebola, is the moniker from 2014. This was very similar for those of you that remember. And we ran this as kind of an ad hoc to see if our system really could work and really could provide information. And what came out of it for looking at public tweets that were the information sources, not those that tweeted the most, but those that were giving the most influential information, we found a couple of the media sources that we would expect. Like number one is CDC flu. That's the Centers for Disease Control and Prevention. And thank God that's up there as a top hit, because that's where you'd expect good information to come from. And there's others that you see. Flu.gov is also CDC. You see top media sources like New York Times, CNN, Time Magazine, other CDC helplines. Over here, CDC Emergency, CDC eHealth. That's all good. But what was surprising was, say, number 3 on this list, official PAX. How many of you have heard of PAX, the conference? Okay, so we hadn't either, but luckily I teach a class and I have undergrads, and I showed them this, and they're like, oh, PAX, that's Penny Arcade. It's a bunch of, I think, pre-adolescent males who like to play video games, and they're in Seattle at this conference, and they're the first group in the US to all contract H1N1. So they started tweeting with each other, hey, Bob, I got it. Did you get it? Yeah, I got it too. Did you go to the hospital? It's diagnosed. Yeah. How bad is it? Well, okay. Well, did you die? No, I didn't die. I mean, these tweets are something else. And so they were given good information that was helping people stay safe. It was, the best information that you could get about this outbreak and how serious it was. It turned out not to be as serious as people thought. It was still serious, but we didn't wipe out our whole population. And we never would have known to even look there or turn our lens towards it without this type of analysis. So in a breaking event, how do we use the information that we have to keep people safe? We've proposed a system like this where we can tune to it. On the other hand, you always need a human in the loop. I showed this slide actually in India. I was on a trip, and I showed group the slide, and there was an Indian student who was a fan of the Backstreet Boys and saw them up here, number 9. So Backstreet Boys, they're a male band out of the U.S. And someone asked, well, why the heck are they on this list, in the top 10? And I thought about it for a while, and I had absolutely no idea. So I said, why don't you tell me? So he actually went, he wrote a paper, he looked it up, and he looked at news events. And it turned out that they were releasing an album about the same time as H1N1. And so people were saying, tweeting to each other, do you have H1N1? And are you getting the new Backstreet Boys album? So, you need a human in the loop, because it's, at the end of the day, what we're trying to do is take a massive number of alerts that would go to a human analyst and try to give them the most important ones, but you still need a human to go through in analytics and really understand why everything is up on that list. So that's sort of a hallmark of what we've done. And the software that we've developed and released as open source from Georgia Tech to do it as kind of a community effort is called Stinger. And it's an analysis package where I've just listed on this slide a number of the algorithms that have come about through sponsored research and through the hard work of my graduate students. We have a number of different operations that we can now do on a streaming graph like this. So you want to be able to insert and delete edges, maintain clustering coefficients, which is often a metric that social analysis analysts like to understand the clustering coefficients. Essentially, that counts the number of triangles and gives you connectedness of communities. Tracking connected components over time, looking at different types of clustering of the data between a centrality that I already talked about. And then there are other types of subgraph extractions, like K-cores are popular among some communities. Doing breadth-first search and searching in the graph is also popular. So what we've tried to do is build up an analysis package where we have a very high-level way for an analyst to make use of these or implement new functions. And in addition to being able to support those functions with a reader process and multiple analytics that are, one writer process and then multiple readers who are running the analytics, we wanted to keep up with very high ingest rates. So for instance, we're now able to ingest millions of edges per second on a graph with, say, 1 billion edges or vertices, and have several analytics running concurrently at the same time on that data structure. The link for it is down at the bottom at georgiatech.cc.gatech.edu/stinger. Or here it is as well. There's a nice web page where we have a lot of the source code and GitHub development plans for documentation, presentations. It's all there. And we have a lot of users for it, so we're trying to make it more solid. And there are both academic users, national labs, and government. We also have a number of the computing vendors that have picked this up as an interesting code, and we've used it with Intel. They're helping to support it, NVIDIA, IBM, and so on. And we also have a number of startup companies. Ionic is one that I'm associated with, and others, MCN, ArrayFire, are using this in part of their analytics, not their core business, but an analytics function. And then we have financial companies like Citibank has been asking us a lot of questions, which lets us know that they have some use for this for their analytics. So the code over time has become more solid, and it's based on some graph structures that we have, also called Sting. And this was a community effort to try to come up with a data structure that turned out to be something that was missing from the literature. So a couple years ago, a group of us came together and tried to come up with a way of representing a streaming graph. Our traditional notions of a graph abstraction just didn't work. We couldn't do compressed sparse row or adjacency lists, adjacency matrices, because our vertex set was changing over time, and we didn't know how many vertices we would have over time. We wanted to have a framework where we could implement, not worry too much about optimizing the data structure, but look at the analytics and their capabilities. So we came up with this thing called Sting, and there are some design goals to it. We decided up front that it was too hard to go to distributed memory first, so we would target shared memory platforms, where today we can go commodity and buy a multi-terabyte server. That's pretty good for many, many industrial class problems. And by assuming a globally addressable memory, we don't have to worry about the hard things like partitioning of the graph and synchronization of various sorts in the graph. We could really just throw the things in the graph and then use the shared memory, exploit the shared memory for algorithms to get a feel for how difficult these algorithms were. The graph data structure Sting looks kind of like the following. So I know it's an eye chart, and you can't really see it too well from back there. But essentially what we have is a contiguous array for vertices. And then for each vertex, we have blocks for the edges. And we put all the edges of a various type into a contiguous array over here. And then they're chained together. And all the edge blocks have header information. So I know how many edges are in each block. I know sort of a high watermark. And what this lets me do is various things. I can work on all the vertices concurrently in parallel. If I want to figure out, for instance, how many vertices do I have colored red, I can quickly compute that. Or if I want to search for edges of a particular type, I can find those blocks very quickly as well. So we came up with, it's not rocket science, but we came up with a data structure that would let us grow the edge set and the vertex set on the fly and not be locked into a fixed number of vertices. We don't know, after all, how many vertices we'll start or end with. And it may shift over time. And then given this data structure, the process is as follows. This is kind of a workflow where we have the edges coming in, inserts and deletes. And we're going to pre-process those batch updates. Those batches could be size 1 or could be 10,000 edges. It's a configurable parameter. And we will sort them, reconcile if we have an insert and then a delete. Maybe we don't put it in the graph. But we figure out maybe we pre-sort them so that we can insert them into the graph more easily. And our graph gets updated. We may age off old vertices that haven't been touched in a long time in the graph. We'll alter the graph with our new view of the world, the edges that have come in. And then we'll look at the affected vertices and update metrics or any of the change detection algorithms. We'll see if they trigger. And we'll iterate around our graph with these steps over here. And if we get answers, we'll flag that there's been some sort of change detection. So the way it works is we have, again, that this is kind of an eye chart over here, but you could think of it as a server running this graph data structure. And on the left of this chart, what we have is different types of information coming in here. We can accept templated JSON parser. We have CSV, so spreadsheets, text, random edge generators, whatever you want. We can hook those in very readily from real-world data sources and inject them into the graph. And then what happens with your analytics, you may have a workflow of analytics that attach to that graph. And those analytics may call other analytics and so on. And then on the outside of this, we just have sort of a demo interface of exporting to JSON and then having an HTTP interface. So you could demo this essentially. Our hard work is really on the analytics, the algorithms, and Stinger. We're not as much a visualization group or one that understands what to do with the output information. So we put it out there, and others can take this and drop it into more of their analytics system where they're better at doing the information visualization. But our hard work right now is this focus of the blue boxes over here of how do we create this graph structure and how do we keep up with these high ingest rates at the same time as running these analytics that we've designed. Any questions? So why not existing technologies? Well, there's traditional SQL databases, but often the types of graphs that we have don't really fit into the structured SQL framework. And then you can find a lot of graph databases. If you go and you look, you'll find a lot of on-disk databases. But when our response time is often in milliseconds, that's going to be nearly impossible if the graph resides on disk. Every time we traverse an edge, we have to go and do another disk access. That's maybe 5 orders of magnitude, if not more, slower than doing things in memory. So we are trying to keep this in a memory abstraction. There's also Hadoop and other sorts of projects that are looking at MapReduce and other programming models. That's not often a good match for the analytics that we have. In fact, many of our analytics, we've never seen anyone been able to implement them in MapReduce, so that's kind of a non-smarter. And then there's a lot of graph libraries and processing tools out there, but often they'll work on graphs with 10,000 vertices, 100,000 vertices, but when my graphs have trillions of vertices, they just fall over. So we need algorithms that are going to be more resilient to errors and are able to scale up to much larger instances. As an example, often you may have an anomaly that's 1 in a million, and on a small graph, maybe you'll find that once every so often. But if I have a graph with a trillion vertices and my algorithm has a false positive rate of 1 in a million, I get overloaded with false positives. So we need to have more resilient algorithms once we go up to this scale. Now, we have a number of results. This is just a catalog of some of our results of looking at clustering coefficients, which is triangle counting, connected components, community detection, doing incremental PageRank, and also between centrality. We have a lot of papers to support the algorithms that we have where we're able to do many of these very, very fast for large graphs. But question? Petaflops and gigaflops, usually 0 because we don't have any floating point other than the timer. But for operations, it's kind of hard to count what the number of operations are. So rather than counting basic operations like a floating point operation where the scientific community often pats themselves on the back when they get 80% utilization of a big resource because they're keeping the processor hot, what we look at is traversed edges per second as a canonical way of looking at our performance, because it's really the memory subsystem, and we have a graph, and we traverse these edges in the graph, and that's a much better, more natural way to count. So there may be a couple operations that take place as we traverse edges. What I do is I'd probably refer you to Graph 500 to take a look at performance of doing breadth first search on a large graph, because that's the place where it's been studied most. Here at the end of the day, we're trying to make an analyst happy. We don't really know what is peak for these systems other than back of the envelope calculation on our memory bandwidth and the latency to memory. Question? So we actually run on different types of graphs. And just to repeat the question, you're asking about whether or not the edges are weighted or not weighted or weighted within a small range. We've dealt with different types of graphs. So here, some of these may not be on the same graph. We have instances of graphs that are weighted, some are unweighted, some have weights that come from integers in a small range, some have weights that are counts, some have weights that are floating point numbers or probabilities. So we've worked, these may not all be on the same graph. So let me give you one case study. I don't have a lot of time left, but one of my students, Anita, is looking at a very interesting problem, and it's called seed set expansion. So given a set of vertices, an analyst may have a big pile of data, and they identify something weird happening here, here, and here. And they ask themselves, are those related? Is there anything happening? You know, they seem to have the same motive. Are they working together? You know, these vertices, what are they? And looking at a trillion vertices, no one could possibly look at it. So what the analyst would like to do is extract out a small community that they could visualize on the screen that best captures those vertices. And we call that seed set expansion. And once they have a set of seeds and they have a community around those seeds, what they would like to do is track that over time. So maybe I'm watching some event and these dots are interesting. As the event unfolds, I want to see, okay, well, are they in cahoots? Are they collaborating with each other? Are they separate? What exactly is going on? And if I can explain what's happening, maybe I'm no longer interested in that seed. I can throw it away. So this is very interesting for law enforcement queries and also other places where an analyst has a couple things, a handful of things they want to track over time. The other interesting thing that we're trying to do is, given a small community, you may have a vertex that is very central in the community. I'd like to automatically detect anytime that central vertex moves from being the core in one community and moves into being core in a different community. So Anita is my PhD student. This is what she's been working on over time, and we have some algorithms now that are able to track these sets of vertices as they change over time. As edges are added and deleted from the graph, we're able to track those communities as they change. So the seed set expansion, there's some results. The font is too small for you to see. But what can happen is that we have sort of a fitness score of how well this is doing. And after a change in the graph, we may find that we have a drop here in the fitness scores. And what we do is we can update the graph. We can prune things off of the graph that are no longer interesting, and do this in sort of a greedy way where we can keep the fitness scores remaining in an increasing way. So there's a paper behind this, but essentially what we're doing is tracking over time, rather than the alternative is every time period, every time we have an update, we could recompute from scratch. But instead, we're really tracking this as updates come. We're trying to see if those edges impact our communities that we're looking at, and if so, update those communities, versus always rerun from scratch. So there's some more results over here that give precision and recall. I'm not going to go through details of these other than just to show you that what we have has some provably good properties to it and is giving us some useful work. I also have another student, Adam McLaughlin, who's been looking at tracking betweenist centrality over time. He's had a couple papers, a best student paper finalist at supercomputing, and he sort of is focused on GPU programming using accelerators. And betweenist centrality, because it's computationally expensive, he's been looking at tracking this over time. And so I mentioned talking more about centrality and betweenist centrality. It's a measure that's been used sort of ad hoc in the community to look at different types of important actors and applications, ranging from terrorist networks to organizational behavior, looking at HIV transmission in jail populations, supply chain management. All over the board, it's been sort of an ad hoc function because it's looking at shortest paths in the graph and trying to find the vertices that sit on essentially the most number of shortest paths. The results that we have, again, the code is available, but we have some impressive speedups that scale linearly up to 192 GPUs. And this work Adam spent the summer at NVIDIA, so some of this work is joint with NVIDIA. And the idea is to take this metric of betweenist centrality, and as I mentioned, you could define it on the vertices or the edges. But on the vertices, you look at all the shortest paths that go through a particular vertex and divide it by the total number of shortest paths. So it's a counting argument in terms of number of shortest paths that you sit on, and computing it exactly is compute intensive. There's a lot of prior work out there on how to implement this, say, for GPUs, one that parallelizes against the edges, another that tries to use fine-grained parallelism on the GPUs, but they both use a predecessor array on the same size of the number of edges. And the number of graph traversals they have is quadratic in the number of vertices plus the number of edges. So what we've done is implemented a strategy that trades off memory bandwidth and work, and the approach looks something like this. We have an input graph, and we're actually have a copy of the input graph at each one of the GPUs, and the vertices are sent out to essentially a grid of CUDA processors on the GPU, and they are running independent searches on those graphs to do this shortest path query, getting partial results, and then using the GPUs to merge those together atomically to get the final results. So we're building up partial results as we go. We're getting the partial results down at the bottom and then accumulating them. So this is a picture where we have a fine-grained traversal downward, and we start at 1, and the blue edges, the darker blue edges are what are explored, and threads are assigned to each vertex. And as we move down, the size of that frontier here may change, where we started with 1, now we have 3, then there's 2, 2, and 1. So we went 4 steps, a depth of 4, and we have a variable number of edges to traverse per thread. Another way to do this would be an edge parallel downward traversal, where threads are assigned to each edge, but there's only a subset that are active. And here we're trying to balance the amount of work per thread. So this is another parallelization strategy. And then the last method that we have is a work-efficient downward traversal, where we're assigning vertices on the frontier, and we're using an explicit queue and have a variable number of edges to traverse per thread. And so just a short view of what happens here. As we're moving down, the work is balanced between vertices and edges in a more explicit way. So those are just different ways to traverse. And it turns out that of those three methods, no one is the best on every graph. So here are a couple graphs. These are iterations through the graph, and the colors represent different graphs, and they all have different performances. So what we looked at was a way to do this where we can dynamically switch between these methods to get the best parallelization possible. And we actually have some good results on a number of different benchmark graphs coming from all different sources. So this is a canonical set of graphs coming from others' challenge problems, essentially where we have on the order of hundreds of thousands to millions of vertices, up to millions of edges. Some are small diameter graphs like social networks. Others are large diameter graphs. And just as one example, here's a Delaney triangularization graph. And this is log of the number of vertices in the graph. So 2 to the 20th is a moderate-sized graph on the right-hand side. And our new method is the method that is in black over here. And this is log of the running time. And so when the graphs are really, really small, we're actually a bit slower on the order of seconds compared to the best method. But that's a really small graph. When our graph becomes much larger over here, we're actually faster, and it's a log-log graph, so it's kind of hidden. But that turns out to be minutes to hours, that difference. So this method does really well. So, well, here's the visualization. This is different in, say, milliseconds, and over here, this is actually, in this example, that's days in this example for this graph. So what we'd like to do is be able to pick the right algorithm for doing this type of streaming traversal. And then we also have some results on multiple GPUs. For the sake of time, I'll skip over the multi-GPU work. I mentioned earlier Graph 500 is a benchmark that's trying to track the performance of new machines on these types of graph problems. And we're looking at a metric called traverse edges per second because it means a lot more than, say, petaflops in terms of analyzing the performance of a system. So if you're interested in benchmarking, there's a lot of information at graph500.org, and I refer you to that. But also, architecturally, it's a very interesting time as well, because what we want is an analytic platform that's able to do these graphs very well, machine learning, database processing, stream processing, cloud, Hadoop. I want all of this stuff, accelerators. We don't have it today. We have point solutions, like what's on the right-hand side. And, so here's some old stream processing from IBM that should excite you. So over here, we have a lot of different technologies, NVIDIA, IBM, Intel Cray, trying to make sure I don't forget any of my sponsors. And what we want to do is have an easy-to-use platform where an analyst can come and use all of that technology together. I think that's the holy grail now for analytics. The architectures are also becoming highly multi-threaded, hybrid cores, and just really, really interesting architectures. We want to be able to leverage those multi-threaded architectures that have heterogeneous cores and instruction sets. And then memory technologies as well are really having some disruptive changes right now that we want to leverage as well. If you haven't looked at IBM, NVIDIA, and other companies, Micron, doing 3D stacked memory, it's exciting. There's Hybrid Memory Cube Consortium, Micron, Intel, et cetera. Programmable logic layers on chip. It should be a P, possibly non-volatile. There's orders of magnitude lower energy costs for doing things inside the memory subsystem. And this is a game changer. I'm always asked what I think the most interesting aspect is today, and it's the memory subsystem. I think that the characteristics of how we program algorithms and keep them energy efficient is really going to be dominated by these memory technologies. Here's a example from Micron on the hybrid memory cube, where this has multiple layers of memory with quite different characteristics and a programmable logic layer right on the chip where I can offload, if I can get it into the architecture of the memory, I can offload some of my functions into that memory subsystem. So it's a really exciting time architecturally to look at these streaming analytics. So to conclude, massive scale streaming analytics is just emerging in its infancy, and it will require new high-performance computing platforms, new streaming algorithms, energy-efficient implementations, but are all promising to solve real-world challenges. So I encourage you to take a look at this space, and mapping the applications that we have to these high-performance architectures may yield 6 or more orders of magnitude performance improvement by getting the right algorithm on the right platform. So I think it will naturally be heterogeneous in design, and it's going to require a different type of set of architectural features. Some acknowledgements. Jason Reedy, my research scientist, and a number of my current graduate students have done a lot of the work here. And then I have a number of alumni who've gone on to bigger and better places. And some of them are at labs, faculty positions, startup companies, and large organizations. So they're all doing well. They're primarily the folks who've done the hard work in getting Stinger where it is today. And then we published a lot of papers. I'll make these slides available to the group here. And we have reference to a lot of the work that we've done in the last couple of years, 2013, 2014, et cetera, in this space. And then finally, we've had a lot of sponsors to this work, some of whom are listed on the slide, both national labs, companies, and other organizations have generously sponsored a lot of the different aspects of the work that we've had over the last few years. So thank you for your attention. I'm delighted that I was able to give this lecture here today, and I'll ask if there's any last questions. Thank you. Any questions? So for Graph 500, just to repeat some of the question, why does GPU matter for Graph 500, and are you looking at just traversed edges per second? In fact, there are many different ways to look at this benchmark. One is graph size. So we're looking for the largest graph that can be solved, and then looking at the rate. And there's somewhat of a direct correlation between size of the graph and the rate achieved. But we're really interested in size of the graph first. Today, the largest entries have 2 to the 40th. 2 to the 40th is large. That's 1 trillion vertices and in order of magnitude more edges in the graph. It's just stunningly large. And a lot of the top platforms are ones where everyone said they'll never be able to do graphs well, like IBM Blue Gene. And in fact, some of the top entries are all IBM Blue Gene systems. So it's been a surprise architecturally to understand how these systems do well. For GPUs, there's a lot of interest because I think GPUs have some throughput capability for stream processing that we would like to leverage on broader scale. For the DARPA Ubiquitous High Performance Computing Systems Program, UHPC, I was partnered with NVIDIA looking at sort of next generation Echelon from NVIDIA was sort of a concept machine of how to create a new system that would do well on various types of applications, including graphs. So there are a lot of features in making GPUs more general, in making them more scalable, et cetera. So we have a lot of interest in looking in that space as well. Just as a general comment, there's multiple swim lanes in high-performance computing. And there are high throughput machines, there are high compute capability machines, et cetera. And we're trying to understand what are the dynamics of all of them in terms of energy efficiency, in terms of capability, to select, as we go forward, will there be one HPC system in the future, 2, one that's good for compute and one that's good for big data? Will there be 3 or more? How will that space shake out? And so a lot of this early testing is try to gain understanding into the performance, into the feedback, the benchmarking, to help influence and understand what are the trade-offs in the architecture. Does that make sense? So it's at a very early age. This benchmark's been around only for about 5 years, and so we have some data to help with that. But I think we're also undergoing a time when there's a lot of interesting architectural innovation, and we're trying to figure out how to take advantage of those artifacts in the architecture. Any other questions? Well, thank you for your time and attention, and